Okay, let's begin. I have, let me see how many slides I have for you guys. 170, so 170 slides. Let's begin. Few things to mention. I have been slightly behind my work, which is why if you see me not being responsive, admittedly it's because I've had to set your final after setting your midterm, and I had to set the makeup midterm. So for the whole week, I've been staring at nothing but questions. So I'll try to be more responsive from now on. But for the last weekend was not good. I've not had a weekend in 3 weekends. Okay, so what was I going to mention? Today we're going to do MST. This is going to be the last graph algorithm. After this, we're going to talk about dynamic programming. So that's just sort of a quick overview. Anything else to mention? Okay, well, we're still grading your midterm, and if you want the midterm solutions, I can release them soon. But the remarks on it will not be accurate because it has not taken into account your scripts. So whatever grading you see on it is not indicative of what we did, right? It's just a hint of like what we tried to do. I'll try to release it soon, maybe this evening or maybe tomorrow. Again, sorry, I've been really stuck with setting your final and the department wants the final script from me like tomorrow or on Wednesday, and I'm like, what, final isn't that soon? But they want it, so I had to do that first. And I'm pretty sure you would want me spending more time setting your final than anything else. Okay, that's about admin from my side, not admin from your side, right? So hold on, why aren't these buttons working? Let's see. Okay, hopefully that works now. Okay, it works now. Housekeeping, business as usual. One thing to mention, right? Some of you still haven't done PS7 Part 1. Please go do it. We extended the deadline to Wednesday. Okay, like I mentioned, the plan for today, the last two graph algorithms you're going to see before we move on to your so-called last chapter on dynamic programming. Okay, why you should care about minimum spanning trees? I don't have a joke for this one. I think I tried to think of one and I forgot about it, so I just didn't put anything in. If you're an AI person, and when I say AI, I don't mean like happy to use like ChatGPT or whatever. AI person as in actually making AI, right? MST is great for clustering. So if you're a data analysis person, if clustering is your thing, MST is your thing. Right? If you ever want to do image segmentation, so okay, I don't have a picture of this. I should have put a picture for you. But if you have a picture, right? Let's say you took a photo of something. How does your algorithm tell what is what? Like, how does it tell the car from the environment? Right? How does it tell the trees from the cars? How does it tell the people from the buses? Right? That's called image segmentation. It's part of image segmentation, right? So how do you actually segment your images? MST is an algorithm that helps you do that. Okay, if you want to parse handwriting, for example, let's say that you take a picture of handwriting and you want to figure out what the stuff is. Again, MST. There are MST algorithms for this. Okay, so there are many reasons why you should study MST. Okay, so now that I've given you reasons, let's talk about minimum spanning trees. Right, so here's your input. You're given a connected, weighted, undirected graph. Okay, and what I need you to output for me is a tree, a connected tree, a spanning tree that is the minimum possible weight. The minimum possible weight over all subset of edges. So here's an example. By the way, does this graph look familiar to you guys? Do you guys know where I took this graph from? 131S, right? Okay, you all know. Like, this is in your tutorial. Actually, we had to do this in your final, like the last tutorial. I think we had to basically trace out the MST for you, right? Okay, so this is actually from your tutorial. So you should know how to do this, right? So for example, here's one such tree. Here's one of your possible MSTs. I know you all had to painstakingly list out all the non-isomorphic MSTs, right? But here's an example with weight 19, right? Okay, I know we did this before. I know we went on the whiteboard and we scribbled on this, right? But trust me, you didn't follow the algorithm. So we're actually going to do that this time around. All right. So how do we solve it? Here are a few ideas. Let me go through one first, which is probably not what you're expecting, but probably what people would love to do. If you were not shown an MST algorithm before, I'm guessing the first thing anyone would try to do, right? Just go through all the subsets, right? Go through all the subsets, check if it makes a spanning tree, right? And somehow remember the total weight, okay? Then basically just output the minimum possible subset so far. Okay, let's just say hypothetically, Aaron didn't. Actually, I don't know who showed you Kruskal's and Prims last semester. I'm gonna say it's Aaron. Let's just say Aaron didn't show you Prims and Kruskal's, right? I mean, I say show you, but let's be real. Did you remember how to do it, right? Okay. Let's say that we didn't show you this, right? I'm guessing this will be one very natural approach, right? Just try all the possible subsets, check whether it's a tree, remember the sums, right? Okay, so before we look, conceptually this is easy. I don't think we're going to talk about this, right? But quick aside, right? Given a set of edges, how do you even tell if it's a spanning tree in the first place? So I give you a graph, right? I tell you it has n nodes, and I give you a subset of the edges, and I tell you, go tell me whether it's a spanning tree or not. How should you do this? Right? So that's an aside, right? Think about it. Idea 1 requires you to be able to do this. Idea 1 requires you to be able to be given a set of edges and somehow tell whether the tree is spanning or not. So how should you do this, right? So aside problem number 1, right? Given a subset of edges S and a graph that has n nodes, I'll put true if the edges is spanning. I'll put false. Why is my false in blue? It should be in red anyway. Right? Okay, I guess false is in blue today. Right? But I'll put true if it's spanning. I'll put false otherwise. How should we do this? How should we do this? Right? So in other words, I need a subset of edges that creates a tree, first of all, and second of all, the entire graph is connected, right? Okay, so here's a graph with 5 nodes as an example. If I give you this, right? If I give you literally this set, right? 0, 1, 2, 3, 4, 0, 2, 1, you're required to output yes. If I give you 0, 4, I think we can all agree this definitely is no. You don't even have enough edges in the first place. Okay? Or even if I give you a set with 5 edges, right? Like you might still have to output no. Right? Why? Well, because actually, if you look at the nodes 0, 3, and 1, they actually create a cycle right there. Right? Okay, well, actually, I just revealed the solution, right? Like what you should be doing. Okay, so here are some observations. Accidentally spoiled it. Spanning trees must have n minus 1 edges. Spanning trees must have n minus 1 edges. Okay, so if you ran BFS or DFS from any of the nodes, we should be able to reach every node in the graph, so there shouldn't be a cycle. Okay, so based on these observations, we kind of have an algorithm, right? Given a subset of edges, literally just run BFS or DFS, find out if there's a cycle. If there is a cycle, you know that this is not a spanning tree. We reject this subset, right? If you don't find a cycle, you know it's a spanning tree. You add up the weights, and now it's a spanning tree. You try to remember the weight and try all of these possible subsets, right? Okay, so let's come back to ideal 1. Okay, let's say that we didn't know prims or Kruskal's, and let's say we really just, really tried to try all subsets of edges E. Okay, and if it makes a spanning tree, we'll remember the total weight, and we'll output the minimum so far, right? If it's not a spanning tree, we don't consider the minimum of this, right? Okay, so let's say hypothetically, no prims, no Kruskal's, like whoever Primsworth and Kruskal's didn't exist in this lifetime, and like pretend you're like this is 40 years ago, so you're somehow born and living before prims and Kruskal's, and now you come out with this algorithm. What is the complexity? What is the complexity of this naive algorithm? Think about it. Option 1, 2 to the power of m time. Not very exciting today, right? We're starting off exponential time. Option 2, n plus 2 to the m time. Okay, no one seems to think so. Option 3, n times 2 to the m time. Okay, I see a few hands. Option 4, n plus m times 2 to the m time. A few other hands. What about the rest? Leave it blank in exam. What would you do? I'm going to run through this again in case you needed time to think about this. Option 1. Option 2. Option 3. Option 4. Okay, I see mostly people talking about option 4. It's option 3. Okay, close. Right? Let's try analyzing this, right? Okay, you go through all the possible subsets, okay? And you pretty much only need to go through the n-1 size subsets, right? So you ignore anything else that is big. You ignore any other subset of edges that's larger than this. Okay? So for each of these, you're going to create an array of size n as usual to run your BFS or DFS. You can convert the subset to an adjacency list that actually happens to run in ON time. Surprise! Right? And then you run your DFS. Okay? So it's going to take ON time for your DFS, for your n-1 size subset. So this is going to be n times 2 to the power of m time in general. Does that make sense? Even if it doesn't make sense, I'm sorry to say, you have to make it make sense, right? You really have to make this make sense. Okay? So I mean, you could say, okay, this is pretty good, like we shaved off a m factor, right? It's n times 2 to the m time. Like, okay, I think we all know we're not here for exponential time algorithms. Okay? Okay, so let's move on to not so naive ideas. Let's move on to now that we're warmed up, I hope, right? Let's move on to not so naive ideas. What if we tried adding edges as long as we don't create a cycle? We're just going to keep adding edges. Okay? Keep trying to do this as long as you don't create a cycle. Keep doing this until you connect the entire graph. Okay? So, question. Let's say that we try to do this. There's something we haven't specified yet, which happens to be what kind of edges we should add. Okay? So again, we're gonna keep trying to add edges as long as it doesn't create a cycle. Do this until the whole graph is connected. Question. If we want to follow through with this strategy, what kind of edge should we try to add into the graph first? Minimum spanning tree, yeah? The heaviest edges, the most expensive ones. Option 2, the lightest ones. Okay, I see a few hands. Less than half the class. The ones that have the lowest ID endpoints. Like, for example, we start from node 0. Okay, I see one hand. The ones that buy us coffee. Okay, great. Some of us are coffee lovers. I guess the rest of us hate coffee, right? Well, please take the cheapest, lightest ones. Those are the ones that you want, right? It's the minimum spanning tree. Intuitively, you should always be taking the cheapest and lightest edges. Also get the ones that get you coffee, I guess. Okay, so we're going to try to do it this way. We're going to try to add our edges based on increasing order of weights. We're going to try to add our edges based on increasing order of weights. Okay, so we need to somehow process our edges based on its weights in increasing order. We're going to try to add them as long as it doesn't create a cycle. Okay, so question, we now have an idea. We now have sort of a rough strategy. The next thing we need to think about is what data structure we should use. Okay, I need you to pay attention to how we came up with this before deciding on the data structure. Okay, so I know like exam strategy would be, is this a tree question or is this a hash table question? Then figure out how you're supposed to shove your solution into a hash table, right? Let's do the opposite because that's how you're supposed to do things. Okay, so we now have an idea on how to solve this problem. The next thing we should think about is which data structure best supports our use case. So question, based on this idea of trying to add edges while still preventing cycles, what kind of data structure should we use? A, adjacency list. B, edge list. C, adjacency matrix. B, child segment tree. I see one hand. That guy's failing the class, right? We need to somehow process the edges in increasing weights. So which graph data structure do you think best supports our use case? Well, it has to be an edge list, right? Because we're going to sort the edges by increasing weight. An adjacency list doesn't give you this benefit, and an adjacency matrix doesn't give you this benefit. Does that make sense? Okay. So for once, your edge list actually is useful, right? It's like the crappiest data structure that actually has a use case. Okay. Okay, so we now hopefully we now kind of know that an edge list is the best way to do things. Okay, we want to process edges in increasing order. The best way to do that is to sort our edge list. Okay, the next thing we need to do is to figure out how to prevent cycles from happening. The first two paragraphs are something you've seen before. You don't have to read that again. Okay, so we now know we want to use an edge list to process our edges in increasing order. We now know that we want to at least try to keep adding edges as long as it doesn't create a cycle. Okay, so we have this thing that we need to figure out how to do quickly. We need to very quickly spot whether adding an edge will create a cycle or not. Okay, so how do we quickly do this? Option 1, just eyeball the graph. Wow, surprisingly, no one raising their hands. But you all did this for 1231S, right? When your TAs drew the graph on the whiteboard, I bet all of you didn't use a data structure, right? All of you literally just looked at the graph and saw whether there was a cycle or not. Then you say yes, no to your TA, right? Okay, good. We know we're not supposed to eyeball it. Why? Computers don't have eyes after all, right? Like this thing, well, actually has a camera, but you don't hold up your laptop to a graph and say like, hey, does this have a cycle? Or not? You don't do that, right? Okay, option 2, DFS. No hands? Interesting. Doesn't DFS spot cycles? Option 3, ask it very nicely. I see a few hands. You can also ask your exam papers very nicely what the solutions are, and we'll see whether it responds, right, in the finals. Option 4, use UFDS. I see a few hands. Option 5, use a visitor array. I see a few hands. Okay. Well, the answer is actually, you could use a DFS. Actually, it wouldn't be quick, but you could use DFS to spot a cycle, right? For example, let's say that I have this graph. Again, it's your tutorial graph, right? So you should be very familiar with this, right? Let's sort the edges in increasing weight, right? So I've literally have I sorted it for you already? Yes, I have. I've sorted it for you. Okay, so we're going to process the edges in increasing weight now. Okay, so if you process the first edge and you ran BFS/DFS only on this edge, there is no cycle. That's fine. We're going to take it. Right? We're going to confirm it as an edge that we want, right? Do the same thing again, right? Add another edge. Now in your graph, you have 4 nodes and 2 edges, okay? So you have the AC edge and the DF edge, okay? No cycles here. If you ran DFS will literally say, dude, no cycle, right? So you can definitely take this edge, right? Take that edge. Same thing as before, right? You add this thing in. I know all of you are eyeballing it. I'm eyeballing it too, right? But trust us, if you ran DFS, this is what would happen, right? DFS would tell you there's no cycle, right? So it would basically say no cycle. Okay, we're fine. We're happy. We take this edge. Get the idea? We're basically going to keep doing this, right? So you add this edge. I have a question. If you ran DFS now, would it report having a cycle? No? Who says no? Who says yes? I see one hand. You eyeballed wrongly. The answer is no, there is still no cycle. Right? Eyeball more, or eyeball some more, right? Okay, so we're gonna keep going, right? So that edge also no cycle. DFS would say no cycle. We're gonna add that in. Okay. Question: I now have this edge, right? This C to D edge. Okay. If we added this in, would DFS report having a cycle or no? No, no cycle. Yes, there is a cycle. There is one, right? Okay, for sure. Again, we're all guilty of eyeballing, but there definitely is a cycle. Yeah, be honest, right? You eyeballed, you didn't run DFS, didn't you? You eyeballed it, right? Okay, yeah, the answer is yes. I'm not going to ask you. The answer is yes. Okay, because DFS reports that there is a cycle, what that now means is that we are not going to take this edge in. Okay, so this edge is going to be, this edge is not part of our MST. It makes sense, right? If you threw it in, are you still computing MST or computing minimum weighted something? Definitely not an MST for sure, right? Okay, so we don't want this edge. Okay, okay, yeah, I know, Eldon, you already put this on the slide. You know, okay, yeah. So if you ran DFS on these set of edges, you know, you'll find a cycle, so we don't include this edge, right? So on and so forth. So this one no, that one no, this one yes. Okay, I have a question at this point. Let's say that of my 1, 2, 3, 4, 5, 6, 7 node graph, 7? Yes, 7. Out of this 7 node graph, okay, out of the edges that we've added so far, I have a question. Do we need to look at the remaining edges? Do we need to look at the remaining edges? Who thinks yes? Who thinks no? Okay, great. We don't actually have to look at the remaining edges, okay? Who put that in? That wasn't, must be my, okay. Right, okay. So, we don't need to look at the remaining edges anymore. Even if you did, you would pretty much find that for all of those edges, the answer is always going to be yes, there is a cycle, right? If you try to add them in. Okay? So it turns out that you all should know this, but a tree only has a spanning tree has exactly n-1 edges, right? So the moment you've added n-1 edges, you don't have to look at any more of the remaining edges. Does that make sense? So we can literally stop at n-1. Okay? So here's kind of the idea. I forgot to color this, sorry, so no color today, right? Right, sort the edge list based on weight, create an empty edge set T, right? Then basically for all of the edges, try to add it in, run DFS if there's a cycle. If there's a cycle, remove it. We don't want this edge. If there isn't a cycle, you know, just leave it in. Then keep repeating this until the size of the set is n-1. Let's say we came up with this. Let's say we came up with this. What's the runtime? What do you think the runtime is? Option 1, m log m. Option 2, nm log m. So many n's and m's. Option 3, m log m plus nm. Option 4, m log m plus n squared m. Lots of n's and m's, right? Okay. People don't want to commit today. Okay, well, the option seems to be 3. Okay, here's why. Based on this algorithm, it's true that sorting is going to run in m log m, because you have m edges after all. Okay, creating an empty edge set, to me, that's free. That's one time, you know, whatever. Adding an edge into the set, you know, if you use a hash table, well, I mean, I don't know what you're going to use right now. You haven't confirmed that yet. Okay, but think about it this way. The most important part is your DFS, right? If you're running DFS on an edge list, that's not going to take m plus m time. That's going to take nm time. This is something that we mentioned before, right? Your data structure for your traversals matter. If I give you things in an edge list, your DFS is not going to run fast. It's going to run in O&M time. Okay? If you had to run this for n iterations, that's literally going to be n squared m. Okay? So if you did this with an edge list, your runtime is going to be n squared m. I know you're probably thinking to yourself at this point, okay, but if, you know, Eldon, you can agree with me, right? If we converted this edge list into an adjacency list, it would run a bit faster, right? I completely agree with you, okay? But let's try to be a bit better, right? Yeah, so again, if you're more careful with this, you could have converted the edge list back into an adjacency list. That would have taken O&M, right? Then this algorithm would probably run in m log m plus nm. A bit of an improvement, I agree with you, a bit of an improvement. Okay, but wait, there's more, right? Oh wait, hold on, why isn't this sticker removed? Damn it. Okay, yeah. No, actually hold on, that sticker is supposed to be there. Okay, good, yes. Okay, so let's come back to this idea of spotting whether there is a cycle in the graph or not. Okay, DFS works, and you saw the time complexity, right? So you saw the time complexity, okay? But maybe we can try speeding this thing up even more, okay? So, okay, we all know it's not option 1 or option 3. I'm not going to play with you guys, right? Option 4, we should use a UFDS to quickly spot whether there's a cycle or not. Option 5, use a visited array. Okay, so unfortunately to the ones who said use a UFDS, you're absolutely right. You should be using a UFDS. For the ones who said use a visited array, I'm sorry, it doesn't quite work. That works for a different algorithm. You'll see why in a bit. Okay, so here's a new invariant for our algorithm. Instead of running DFS, here's a new invariant. We're gonna slot in this UFDS data structure, and the way that it's gonna work is that we want this UFDS data structure to represent something for us. Okay, so there is going to be some semantics involved. I know, throwing out big words, right? I'll use smaller words now. Here's the idea. At every iteration, we're going to try to get this UFDS to help us remember which nodes are in the same connected component. In other words, any nodes that are connected in the graph, in your subset of edges, okay, are also in the same disjoint set in your UFDS data structure. That's the idea. Okay, so this thing is going to try to help us remember which nodes are in the same connected component or not. Okay, so welcome to Kruskulls. Oh, by the way, every time I see Kruskulls, right, I think of like how many of you watch SpongeBob? You know Krusty Krab? Like every time I see Kruskulls, I keep thinking of Krusty Krab. I have no idea why, right? It's just a thought in my head. So I'm gonna curse you with that knowledge now. Every time you see Kruskulls, you're gonna think of Krusty Krab as well. Anyway, so here's what we're gonna do, right? Here's the algorithm so far. Okay, we're gonna basically create our UFDS for n nodes. Okay, and we're basically going to sort the edge list based on weight, as usual. That was from before. Okay, we're going to create an empty edge set T. Okay, and we now want to process the edges in increasing weight order, right? So basically, now that it's sorted, we're going to go through all the edges, UVW. Okay, and well, we made a UFDS data structure. We might as well use it. Okay, so we're going to ask our UFDS data structure whether two nodes U and V happen to be in the same set or not. Okay, so question, what should we put in blank A? What should we put in blank A? So if I ask UFDS, or if you ask UFDS, the data structure, hey, nodes U and V, are they in the same set or not? Okay, what should we do if it says yes? Option 1, ignore this edge. Option 2, condemn it to oblivion. Option 3, add it into set T. Option 4, just remove it. Right? Which option do you think goes into blank A? Option 1. Okay, I see a few serious people. One person raised his hands for option 1. Option 2. Some people love option 2. Option 3. One hand. Option 4. A few hands. Everyone else too shy, don't know what to do. Right? Well, 1, 2, and 4 are all correct, right? Basically, if it happens to be in the same set, it's going to be in the same connected component. You shouldn't be adding this edge anymore. If you add it, you're going to create a cycle. Okay? So continue, don't add the edge into T. Yeah, I gave you 3 options, and yet people aren't participating. Why? There's 3 options. It's 3 times the amount of participation, right? Okay, what about in the other case? So what if you ask UFDS, and UFDS looked at these 2 nodes and said, they're not in the same component? What should we do? Option 1, add it into T. Well, yeah, that's kind of like the opposite thing, right? There's only 2 things to do, right? You either put the edge into T or not, right? Option 2, ignore the edge. No, right? Option 3, do we union U and V? What do we think? Few hands. Okay, interestingly, some people who raised their hands for 3 didn't raise their hands for 1, right? So you only union it, and you don't add it into the set, then what are you doing, bro? Right? Okay, so you need to do 2 things. You do 2 things, right? You need to add the edge into your spanning tree T. You also need to union it. Remember, the data structure needs to remember for you when 2 nodes are connected. Okay, so it's not enough that you add it into T, you also have to union the data structure. And vice versa, don't forget to just put in the data structure, you have to add into T. Okay, so you can intuitively try to think of it this way. You have your set T, which tries to remember your set of spanning tree edges for you. You have UFDS as a separate data structure that helps you remember the state of connectedness. Okay, these 2 things now come hand in hand. You need to maintain both at the same time. Maybe that's a 2030S thing, I don't know, but yeah, anyway, right? Okay, okay. Usual question, how fast does this run now? Not that Kruskull himself has legs, but his algorithm doesn't. How fast does it run? Option 1, m times the inverse Ackermann of n. Option 2, OM. Option 3, m log m. I see a few hands. Wait, hold on. Why is the option repeated? I guess I'll ask again. Option 4, m alpha n. Anyone want to? Oh, sorry. It was alpha n versus alpha m. Yeah. Let's be real. Does it matter? I don't know. All right. Okay. No takers. Congrats! All of you who raised your hands are right. All of you who didn't raise your hands aren't wrong, but you aren't right either, I guess, right? M log m, right? Why is it m log m? Let's think of it this way. It's true, what I told you last week, UFDS takes inverse Ackermann time, so that part wasn't a lie. I didn't take that back, but don't forget, you kind of have to bottleneck yourself with the sort, right? Okay? The sorting itself takes time as well. Okay? So no matter how fast your UFDS runs, like, I'm sorry to say, the sorting really is your bottleneck here. Okay? So we came up with an amazing data structure only to be bottlenecked by merge sort or something from week 1, right? Or week 2, right? Okay? So your time complexity is m log m. Your time complexity is m log m. Okay, so let's continue on with so-called quote-unquote not so naive ideas part 2. Okay, part 2 but idea 3, I suppose. Okay, what if we tried to do something similar, but this time instead of trying to just add edges at all, okay, what we might want to try to do is something similar to Dijkstra. We're going to start from some node S, okay, and we're going to try to grow a tree starting from S. So instead of just adding edges like randomly throughout the graph, we're going to try to add edges that are adjacent to S. Okay, we're going to look at all of the edges incident to our tree. In other words, all the edges that leave our tree. Okay, and take the next cheapest edge that doesn't cause a cycle. What if we tried doing this instead? Okay, so here's an example for you. Right, so let's say that I have same graph as before, really same graph as before. Right, okay. Question: which edges here are incident to our initial node? Okay, I know I said S, but it's A here. Okay, so it's like that's our initial node A. Okay. Question: which edges are incident to our initial node here? Okay, I don't actually have options, so I guess I'm just gonna like randomly ask now. AB, is AB an incident edge? Yes, no, yes. DG, is DG an incident edge to our initial node? No. Okay. CA, is CA an incident edge to our node? It is, right? Okay, I try to flip it around to see how many. Okay, anyway, you all get the idea, right? Okay, so we have 3 incident edges here: A, B, AD, and AC. Okay, again, as usual, we're going to try to take the cheapest edge that doesn't cause a cycle. Okay, in this case, between those 3 edges, this kindergarten stuff, right? What's the smallest number? Look at even single digits, right? Actually, I don't know if they do this to kindergartners. Can you just imagine if someone like a kindergarten teacher just brings this to a kindergarten school and tells a bunch of kids like, hey, which is the cheapest edge? Anyway, right? Okay. So take the cheapest edge that doesn't cause a cycle. If there's more than one cheapest edge, take any. Does it really matter? Right? Okay. So let's say I take this one because I like that one for whatever reason. Right? We'll take AB3. Okay. Now that you've done that, you need to add all of its incident edges. Okay. So go through D and E and basically add them in. Right? So you have 2 more edges here, both of weight 3. That happen to be BD and BE, both of weight 3. Right? And rinse and repeat the process. So take the cheapest edge that doesn't cause a cycle again, right? So for example, yes, we are eyeballing it, right? But for example, let's say you want to take BD3, which if you don't want to, I'm sorry, too bad, the slides were made that way, right? So we're going to take BD3, right? And add all of its incident edges, right? So for example, the 3, 6, the 3, 6, 2, and the other one, the 3 weighted edge, all of them are added in now. Okay? That's the idea, right? So that now they're colored blue. Okay? Basically keep doing this, rinse and repeat doing this, right? Okay, so take the cheapest leading edge again, right? Add all of its incident edges again, and pretty much keep doing this, right? So take another edge, add a bunch of incident edges. All of them have been added. We don't have to add them again, I guess, right? Okay. Question. At this point, right? Let's say that I've processed some of these edges, and I'm looking at the AC edge. Okay, so the edge between nodes A and C. Okay. I think you all know we can't take this edge because if we do, it's going to cause a cycle. Okay? Same question as before. We can't take this edge. Okay? What data structures can help us quickly identify this? Option 1, UFDS. Okay, a few hands. Option 2, an array. No hands? Few? Okay, a few hands. Option 3, a tree. Well, a tree is not even a data structure, dude. Well, a tree by itself is not a data structure, right? So what are we on about, right? Okay. The best option here would be an array. Okay. So I'm gonna have an array. I'm gonna call it int tree. You can call it whatever you want. You can call it blah blah or like hot dog or like burger. Okay, I'm a bit hungry, but you can call it whatever you want. I'm gonna call it int tree. Okay. Here's the intuition. Okay. If you mark nodes as being in the tree, but the moment you come looking for come looking at this edge A and C, you're going to notice that both nodes A and C, both of its endpoints are already inside the tree. Okay, so if you already have two nodes that happen to be inside the tree, what happens if you try to add another edge? You cause a cycle. You cause a cycle, right? Okay, so you know for a fact that both of the endpoints are in the tree. I'm sorry to say, adding another edge is simply going to cause a cycle, so you don't want that, right? So your in-tree array is basically just going to mark nodes as whether they are in the tree or not. Call it a visited array if you want to. Okay, but basically, again, if both of its endpoints are in the tree, we're gonna ignore this edge. We don't want to add it. Okay, let's say after you're done processing it, add all of its neighbors or whatever, take another edge and so on and so forth, right? Okay, So for example, you take another edge, add more neighboring edges. I'm skipping ahead a bit because I think we all get the idea. Okay, right? Edges, you might notice that edges A, D, and DE are also such that by the time you come around to looking at them, both of its nodes are already inside the tree. For that reason, you want to skip these edges and not add them. Okay, so we don't want to add these edges in. Okay, lastly, again, let's say we take edge 5 because it happens to be the cheapest edge leaving the tree. Okay, so if you do that, right, you'll notice that at the moment of taking it, right, just before taking it, okay, node F happens to be in the tree, but node G happens to be outside of the tree. So this is safe, right? So this is safe. You can basically take this. Does that make sense? Okay. So I'm going to mention something now that I didn't put on the slides, mostly because I don't know how to put this on slides, right? Even though it's kind of my job. You might notice how when I talked to you about Kruskal's, we came out with ideas first and then asked what data structure was good, and then basically use that to support our operations, right? I didn't run through an example first. I pretty much just told you, okay, here's how we're going to do things. Now we show you an example, right? With prints, I've actually deliberately swapped the ordering around. I've given you an idea, and we're running through an example first, and then trying to figure out what data structure would be good along the way. Either way, the common theme here is that regardless of how you figure out how you want to do things, you should probably try to think of it this way. You have a problem to solve, you want to solve it somehow. Okay? There are operations involved. Based on that, try to figure out what is the best data structure that helps you, instead of the other way around. Right? Very rarely in real life, you will look at something and say, okay, I'm going to first decide whether I want to use an array or a stack or a linked list or a tree or a hash table. Okay? I know for exam strats, that's like the best. Okay? But I still hide. Okay, I say best, but actually I don't actually mean best. So if you like, I'm going to retcon that a little bit because some of you are going to come to final exam and say, but Eldon, you said that was the best strategy. No, it's not. It's not. You should really think of it as I want to solve this problem. Which I have these steps that I want to accomplish. Which algorithms and which data structures best suit my needs? You should think of things that way. Okay, I highly recommend thinking of things that way. I was going to say a bit more, but I realized I'll be leaking the final, so I won't say anything more. Okay. Final brain, set it over the weekend. Okay, again, as usual, we can stop after adding n-1 edges. You don't even have to look at the rest. Just throw your data structure away. It's not needed anymore, right? Like after n-1 edges, you're done. You pretty much have all of the edges that you need for your minimum spanning tree. Okay, so now that we know the flow of the algorithm, I ask again because I mentioned this just now, right? Now that we know the rough flow of the algorithm, right? Start from a node, right? Add all of its incident edges. Take the smallest one that's leaving it, rinse and repeat, right? Okay. What data structure should we use to track the edges that we should take? So in other words, we need a data structure. I've literally just said a data structure. I haven't said which one yet. But we're just going to sort of like shove our edges into a data structure and then ask it, hey, give me the smallest one that I need to take, right? Okay, so bear in mind that when we visit a node, we need to add all of its incident edges. We always want to know what's the smallest weight edge, and we also need to remove the smallest one. Okay? So question, based on this workflow, based on this strategy that we haven't decided on the data structure, we now need to do so. What's the best data structure to get the job done? Option 1, BBST. Bubble T. Option 2, min heap. Quite a few hands. Option 3, linked list. Okay, get out. Like, no, right? Option 4, UFDS. Definitely not, right? UFDS doesn't even have a notion of minimum in the first place, right? If you need it, you're going to have to make it for yourself, okay? So either BBST or min heap. Okay, either of these two. Okay, so why do I say this, by the way? It depends on the programming language. So like some of them, like they don't give you heaps. Some of them only give you balanced binary search trees. So I'm here to tell you can use either, right? Okay. So here's an idea. Let's initialize either our balanced binary search tree or our heap. like on empty. I'm going to call it incident edges for whatever reason. I'm just going to call it incident edges, okay? And basically, we're going to initialize an array. Remember, we needed an array to remember whether adding edges will cause a cycle or not, right? So I'm just going to set it to all false, okay? And I need to add the first node in, so I'm going to set that to true. Okay? Basically, just go through all of the incident edges to S, right? And dump them into your data structure, which I'm calling incident edges. It just, okay, look, I know it's in pink. All it's telling you is magenta. Someone's going to tell me magenta. It's in magenta, so really all it's telling you is how many edges are, like which edges are incident to your current tree. Okay? Then basically keep popping from the data structure, remove the smallest one possible, and basically check whether that edge that you just popped, whether both of the nodes happen to be in the tree or not. If it is, skip it, don't add it, delete it, whatever. Actually, don't delete it, but delete it, right? And then otherwise, add the other endpoint in, and all the good stuff, right? Basically, add all of its incident edges in. That's pretty much the algorithm. Does this make sense? Okay. Yeah, I know. It looks like, like newspaper clipping ransom note. Yeah, it looks like that. So that's how I color stuff. Okay, so in the worst case, our data structure here holds OM edges. Makes sense, right? And each removal is going to take log m time. Okay. Also, as usual, for every node, we need to make O degree v iterations because we need to process all of its neighbors, right? Okay. So in the worst case, every edge gets inserted. Each insertion and deletion or extract min, whichever one you prefer, is going to take log m time. Right? Which means overall the algorithm also runs in, surprise, surprise, m log m time. Okay, so now you have two algorithms that solve the minimum spanning tree problem, both somehow having O m log m time. Right? Well, I say somehow, but we kind of derived it, right? So here's how you derive it. Okay, so that's the thing. Okay, we forgot to do something very important. What is it? Can anyone see what we forgot to do that was so important? If anyone has figured it out, you can just shout it out. What have we forgotten to do? Something very important. I heard someone say check, but check isn't quite the right thing. We forgot to do something super important. I'm going to be honest with you, for the first 30 seconds of me saying that, I forgot as well, actually. So like, if not for this slide, I would have forgotten that, I would have just moved on. Okay, are you guys ready for me to reveal the solution? We forgot to add the edge into the MST. So you literally would have gone through all of the edges and done nothing. Like you literally would, like your poor algorithm, right, would have literally just created an array, like a binary search tree or whatever, dumped a bunch of edges in, removed it, and we would have gotten nothing out of it. No MST, no nothing, right? You would have just done a lot of work for nothing, which is like basically, a lot of office work out there, right? They just, I literally just shat on office workers for no reason. Some CNN article is going to come out. NUS lecturer making fun of office workers in Singapore. Okay, right? One thing we forgot to do, we forgot to add an edge into the MST, right? Okay, so please don't forget to do that, right? Please basically add the edges into a set, collect it somewhere, like return it to the user, right? The return type should not be void, okay? But basically, this is Prim's algorithm. This is Prim's algorithm. Does that make sense? Well, I'm sorry if it doesn't make sense. You have to make it make sense. But this is Prim's algorithm. Okay, I'm debating with myself whether I give you the break now or later, because now I have two big chunks remaining. So do I do it? Let's do it now. Let's go now. Okay, so it's time for us to go back to doing proofs. Yeah. I censored it just in case, don't want to lose my job, right? Okay, so we haven't really spent time talking about greedy algorithms, and for good reason. Okay, it's quite rare in 2040S for me to give you a problem that's solved greedily. There's a reason for that. I think some of my colleagues might be very happy to just give them to you, but I don't, because I haven't taught you how to prove greedy algorithms are correct. I haven't shown you the formalism of what constitutes a greedy algorithm. By the way, greedy, right, is very, very easily misconstrued. So if I don't know if you're taking 3230 or if you're going to map it to a different module, but there's many things I need you to remember, right? Okay. Here's one of the other things I need you to remember. Greedy doesn't necessarily mean do what you think is right. There is actually a proper formalism, a mathematical formalism for greedy. Okay? Before you know what a greedy algorithm is, we need to show you what optimal substructure is first, which happens next week. Which happens next week, not this week. Okay? So I'm gonna put the cart before the horse for a second here. Okay? Now that I've shown you Prims and Kruskal's, these are actually quintessential algorithms for the greedy, how to do a greedy proof, how to prove that the greedy, prove that a greedy algorithm works. Okay, these are quintessential algorithms to show you something called the exchange argument. So I'm going to show that now. I'm going to show you how to do this. Okay, specifically, I'm showing you specifically for prims and Kruskal's, not in general. So you can generalize this to solve even more problems, but I'm showing it to you specifically for prims and Kruskal's. We're going to do something called the exchange argument. Yeah, okay, that's Roy Mustang anyway. Okay, here's the general vibe of doing a greedy proof, right? Or rather, okay, I'm going to stop calling it greedy proof. I'm going to start calling it exchange argument. Okay, here's the general vibe. Okay, to show that our algorithm is correct, we're going to assume that it made a mistake somewhere. We're going to assume that somehow, along the run of our algorithm, somewhere, someday, it just made a mistake. Okay. So to say that it made the wrong choice, okay, the idea is going to be that there has to be a correct one, right? There has to be a correct choice that it should have made, okay? We're going to swap our algorithm's so-called quote-unquote wrong choice for the optimal choice, the so-called purported optimal choice. And then we're going to try to show that, hey, if you made this swap happen, it actually didn't ruin anything. Everything was still fine. That's why we call it the exchange argument. Okay? As long as we show that things are always fine, despite the fact that we made this swap in choices, okay, somehow we're still, let's say, equal to the optimal solution, then it isn't a mistake, that's a contradiction. Okay? We're going to do a proof by contradiction. It's actually a proof by contradiction. Happy error noises. Okay. So let's do this specifically for prims and Kruskal's. Let's do it for Kruskal's first. Here's the high-level idea. Okay? I'm going to assume that the tree T produced by Kruskal's is wrong somehow. Okay, so we designed Kruskal's algorithm, and we said, okay, I claim this algorithm always produces the minimum spanning tree. We're going to assume somehow that the tree produced by Kruskal's is wrong. Okay, so what that means is that there has to be an optimal minimum spanning tree. I'm going to call it T star. Okay, I'm going to call it T star. That somehow costs less. We somehow have an optimaler minimum spanning tree, whatever that means. Okay. So what we're going to try to do, high-level idea now, is that we're going to try to inductively swap out edges in T star for edges in T. Okay, so I'll show this to you. Don't worry, there will be pictures. If you have the pre-lecture release, you already know the pictures are coming, right? Just hang on, okay? So the intuition is that we're gonna say, okay, someone claims Kruskal's is wrong. Like assume Kruskal's is wrong. So okay, it's wrong. That means that somehow there is an optimal tree. Give me the optimal tree. I will start slowly moving out edges from the optimal tree, and I will show you that every time I do one of these edge swappings, right, the cost will not decrease. The cost will stay the same, and at the same time, we will eventually reach the tree that Kruskal's produces. So Kruskal's could not have made a wrong choice because it somehow still produces one such optimal tree. Okay. So again, we will start with T star, the optimal tree, and keep swapping out edges until we reach T with the same cost. If we do that, since T has the same cost as T star, they are both optimal. Okay? So we're going to assume that the cost for Kruskal's tree to be wrong, it must be the case that the optimal tree's cost is strictly smaller than Kruskal's tree. Okay? So cost T star is smaller than cost T. Agree? Okay, even if you don't agree, I'm sorry, the slides are going to continue, right? But I hope you agree. I really hope you agree. Okay? So there has to be some edge E that happens to be in Kruskal's tree that is not in the optimal solution. There has to be some edge they disagree on. There has to be. Right? Think about it this way. If both the trees were the same, they obviously have to cost the same. Right? Ain't no way. Okay? So T must have some edge E that is not in T star. Okay? So let's look at Kruskal's when it just added edge E. Okay? Let E be the edge that was just added by Kruskal's. Okay? I'm going to let A here be the connected component that all nodes U were connected to at the time of adding this edge. Okay? I mean, you don't have to run DFS, it's just a definition, right? I'm just saying, look, let's say this is the edge that was wrong, right? Okay, so Kruskal's adds this edge. We're going to say, okay, pause, before you add any more. I'm going to go through all of the connected component, go through all of the nodes that U is connected to, shove them in some set A. Any other edges, any other nodes remaining, I'm going to put them in set B. So this really is the picture of a whole graph, for whatever reason, okay? Claim 1, it's impossible to have another edge, E star, right? A cheaper edge from A into B. From A into B. It's impossible to have this happen, okay? Why? Let's think about this. If it did, Kruskal would have seen that edge first, because we did sort the edges by weight after all. Okay, so if it did, Croskell would have seen that edge first and realized that it would not cause a cycle, it would have just added E star instead of E. Okay, so one thing I want to mention, so in 1231S, do you guys remember when you had to do like by definition of something? Like, like when you did some, like, you did a proof, right? And then at some point you say like by definition of function f, or by definition of relation R, okay? If I had to do this proof formally, right, I would literally say by definition of Croskell. Your proof literally has to whip out a definition of an algorithm. I don't know if you think that's cool. I think that's cool. Like, you literally have to go by definition of Croskell. We would not have added edge E, right? We would have added edge E, sorry. Okay? Well, furthermore, since optimal MST T star is a spanning tree, right, it must somehow still connect the two nodes, U and V, somehow. Remember, E was the wrong edge, right? But still, U and V, not U, but the node U and node V have to be connected somehow, okay? Just not via edge E, okay? An optimal minimum spanning tree still is spanning after all, okay? So it must have used another edge E to cross over these two components. Right? It must have somehow had an edge that it used instead, okay, to cross over from connected component A into subset B, somehow, okay? Okay, well, let's consider a new tree, T prime. What is T prime going to do? T prime is going to remove E star, the so-called edge that it used to cross this cut, okay? It's going to remove E star, and it's going to swap it out for E instead. It's going to swap it out for E instead. Okay, so notice that T star is really just us removing one edge from the optimal tree T star. Oh, sorry, T prime, right? T prime is really just the tree that you get from removing E star and adding E. Okay, so you start the optimal tree and you said, okay, I'm going to look at this E star edge that you have that connects these two components. I'm going to literally throw it out and add edge E in instead, which is, by the way, the edge that is accused of being non-optimal, the wrong choice. Okay, so what does the cost look like now? Okay, well, we know from the previous claim that the weight of the E edge has to be less than or equals to the weight of the E star edge. It has to be. That was what we proved just now. Okay, so how does what does the cost of T prime look like? Okay, well, the cost of T prime just happens to be the original tree. I'm going to stand up for this, right? The original tree, the original optimal tree, okay? But you remove the E star edge and you add in the E edge instead. Okay? While doing that, think about it this way, right? Since edge E only costs less than or equals to E star, you couldn't have increased the cost. If anything, you could only potentially decrease it. Okay? This is just basic algebra, right? This is your BBA in 121S, actually. Okay? So what have we done? We've now created a tree, T prime, which happens to have one edge changed from the optimal tree that actually has less than or equals to the cost of the optimal tree. Less than or equals to the cost of the optimal tree. Well, the tree T star, by our assumption, is optimal after all. It is optimal after all, okay? So the fact that the new tree that we have, T prime, is less than or equals to T star must mean that the costs are actually the same. You can't get any smaller. It is optimal after all. Okay, so T prime now is a tree that also costs the same optimal amount, but with one edge swapped out. Okay, we are literally trying to slowly morph T star into our Croskell tree T. I've been saying T a lot, right? But basically that's the idea. Okay, if T prime happens to actually be equal to the Croskell tree, we're actually done. Right? The cost of the Croskell tree is actually the same as the cost of the optimal tree. That's a contradiction. Right? We assume that Croskell was not doing the optimal thing. Okay? So the only case that must happen is that somehow after swapping this edge, we still don't have the Croskell tree. Okay? Just basically rinse and repeat this swapping argument between T and T star. And T prime. Because T prime is also an optimal tree, we can use that one instead. Right? Do this argument often enough. In other words, if you repeat this argument n-1 times, you'll realize eventually you'll start from an optimal tree, swap edges out, always stay optimal until you hit the Croskell tree. Okay? Just repeat this argument n-1 times. I mean, I don't actually control C, control V n-1 times. I just mean that, with a little bit of hand waving here, right, you literally get your Croskell tree. It's optimal. So Croskell is actually going to produce for you, guaranteed, the optimal minimum spanning tree. This is the proof. Okay. We could also do this, a similar approach for proof for prims, but I'm going to show you the exchange argument in a different flavor. Before I do that, I do think that I'm going to actually give you guys a break here first instead. Because if not, you're all going to be dead before the next section. So how about you guys go for a 5-minute break, come back, and we'll do an exchange argument for prims instead. Okay. Proofs part 2. Okay. What I showed you for Kruskal's also works for prims, but instead of showing you the exact same proof, since you've already seen it, I might as well show you a different one. Okay, so I'm also going to do the exchange argument again, but this time around it has a bit of a different flavor. So the first one that you've seen, the first proof that you've seen, the way that it does it is that it literally says, look, I have two trees, one that's supposedly optimal and one that's my tree, right? And then you slowly swap it out into creating your own tree, right? Maybe you don't like the fact that you have to repeat the argument n-1 times, because that was a bit hand-wavy, right? So there's a different way to do this. Okay, high-level idea, again, as usual, you have to assume by contradiction that that your algorithm is wrong somehow. That's how this goes, right? Because if your algorithm was correct, there's nothing to prove the algorithm is correct, right? So we're going to assume that your algorithm is wrong somehow. Well, I say yours, but it's not yours, right? It's prims, right? Okay. So again, we're gonna try to say that at some step, prims, still made the wrong choice. It still chose the wrong edge somewhere, okay? And we're going to let E be the earliest such edge. So it made a sequence of choices. Okay, I really can't stand. I really can't stand. It made a sequence of choices, and basically, at some point, it's gonna start making mistakes. They could make more than one mistake, right? You could make like 5 mistakes. You could make like n/2 mistakes. Okay, we don't know where it made a mistake. I'm just gonna say E is the earliest, the first such edge where it made a mistake. Okay, we're then again going to show that if we didn't add this edge, we're going to somehow arrive at a contradiction. Okay, which means that there can never be such an edge. Okay, so we're going to have a sequence of edges. Let's say E1, E2, E3, all the way to En-1. These were all added by prims in some specific sequence. Okay, and we're going to assume that the tree T defined by these edges is not minimal. In other words, it's not a minimum spanning tree. It's not a minimum spanning tree. Okay. We're going to let T star be an optimal, there will be pictures. We're going to let T star be an optimal tree that has the most amount of common edges possible with T. So there could be more than one optimal solution. We will just pick the one that has the most common edges. Okay, the one that agrees with T the most. Okay, again, prims must have made a mistake somewhere, right? The man himself must have made a mistake somewhere. Okay, so I'm just going to call EI the earliest such edge where there was a mistake. Okay. And basically, up until then, everything agreed with T star. Really, EI is the first part where there was a mistake. Okay, so we're gonna call the edge UV. So it's gonna connect two nodes again, U and V, right? Okay, and we're gonna let S be the spanning tree from the source. So remember, prims grows the tree outwards, right? It basically starts from a source node and it starts growing a single tree outwards. Okay, so we're gonna let S be the spanning tree that's starting from. Okay, I say spanning, but what I really mean is just the spanning tree so far. Okay, so far that basically connects the source to U and everything else. Okay, so this doesn't contain all of the nodes. There could still be other nodes out there, but up until the point of adding E, we're going to pause and say, what is the tree that you have so far? Let me see, right? Okay. Now, since by our assumption, UV does not happen to be in the optimal spanning tree, okay, there has to be, again, as usual, another path that connects from node U to node V. It is, I mean, the optimal spanning tree still has to connect these two somehow. There has to be a path between them. Same flavor as before. Okay, so there has to be some other path. Okay, let's look at that path. And we're basically going to say, look, I don't know how you got from node U to node V, but there has to be at least minimum, like one edge that leaves. Well, actually, not at least one. Exactly one edge that leaves from your subset S, from your spanning tree S, right? Leaves it to connect to V somehow. Okay, so the edge that sort of like starts from the inside and ends on the outside, I'm going to call that like the edge xy. Okay, so based on the optimal spanning tree, that happens to be the one that you're supposed to take instead, right? Okay, again, to do so, there must be some edge exy that basically leaves S. Okay, so same thing as before. Let's consider a spanning tree T prime where we remove edge E and we add in E from T. So again, here's where the exchange happens. This is something that's a common theme with all like proving a greedy algorithm is correct. You're going to do an exchange somewhere. You're going to be like, oh, maybe I went wrong, and if I did, right, you do a swap, and somehow everything is like, haha, it's fine. Everything is actually still correct. Jacuz. Anyway, right, that's kind of how this goes. Okay, so swap the edge out, and we now have a few cases to think about. We literally just swapped E star out for E. Okay, so case one, right? Edge E happens to have a lower weight than E star. If it does, we somehow obtain the more optimal solution. We still have a tree, by the way. Okay? Like we literally removed one edge, disconnected it, and added edge V, right? Think about it this way. In the original tree, X had to go to V, right? We're now basically disconnecting the two of them, and now I'm just drawing an edge from U to V instead. The entire tree is going to be reconnected, by the way, okay? But somehow with lower weight. That can't be true because apparently we assumed that Prims was wrong, right? So this can't be true. We couldn't get a smaller tree out of doing this. Okay, case two, right? Well, they could have the same weight, Eldon. Like, okay, sure, right? So if they could have the same weight, right? T prime has more common edges than T star. That's a contradiction. Okay. Remember, we picked T star for a reason. That's how we picked it. Okay. Case three. The weight of the edge is even larger than before, right? So in other words, like the E star edge is somehow cheaper than the E edge. Well, by definition of Prims, okay, we would not have chosen edge E. Our algorithm would have required us to pick edge E star instead, right? Since both of them are leaving your so-called spanning tree up until that point, neither of them would have created a cycle. By definition of the algorithm, we should have picked E star instead. Okay, literally by definition. So this also leads to a contradiction. So in all cases, it is shown that you can obtain a contradiction. Okay, if in all three cases you do, there's only one conclusion from this: Prims wasn't wrong, right? Pretty much. Does this make sense? Okay, it's gonna take a while for it to sink in. I don't expect you to understand this immediately. Like this proof by contradictions are always like very scary, right? But this is how you can do the proof. Okay, so this is another way to do the proof to prove that Prims is correct. Yeah. Okay, so let's try going even faster. I don't mean me speaking. I mean faster algorithms. Okay, so I'm going to show you a trick now. Okay, so up until this point, I've proven to you that Prims and Kruskals is correct. So you're happy. N log M algorithm sounds pretty great. Okay, let's try going even faster. So what if I really want MSTs, right? What if you're really an AI person or a, image segmentation person, right? And you really want to get these things out fast. Okay, so I'm going to show you a technique specifically for Prims and Kruskals that actually works for other algorithms as well. So it works for Dijkstra. So in other words, take what I say here today. You can literally apply it, the same technique to Dijkstra. You will get a faster Dijkstra. Okay, yeah, I'm going to show it to you for MST finding. Crucially, we're going to make this assumption. We're going to assume that the weights are integers and bounded, so no fractional weights. I mean, okay, look. Before I show you this, right? Think about it this way. I show you an example of integers, right? But there was nothing stopping me from putting root 2 or like, okay, root 2 is a bad example, but like 1/5 or like 2.7 as your weights, right? There was literally nothing stopping you from doing that. You could store fractional values in your binary search trees if you want to. Like, there's nothing stopping you from doing that. Okay. But for the sake of an example, it's usually easier that way. For this section, I'm going to show you faster algorithms, and very importantly, we need to assume that the weights are integers and bounded. Okay, there are still ways around this. Okay, but to make things simple, I'm going to assume that the weights are integers and bounded, and so should you. Okay, so how do we go even faster? Let's assume that the non-negative weights of your MST. Okay, when I say non-negative weights here, what I mean is that the MST has no negative weight. So I literally mean they're all positive, and they're all less than C for some constant C. Okay, so let's say that the weights are all integers, they're all between 0 and C. Okay, can we somehow beat M log M? Can we somehow come up with an even faster algorithm? Again, this is not specific to MSTs, this also works for Dijkstra's. Okay? Let's think about how we can improve our existing algorithms. I gave you a bunch of algorithms, right? Instead of just like really coming up with a new one on the spot, the first thing you should probably try doing is to ask yourself, where does this algorithm break, right? Or where can I speed this up, right? Like you should look at algorithms that you know, and you should say, okay, I know this is an algorithm, right? Somehow it's not making use of this property, not making use of this assumption. Can we somehow learn from this algorithm and make a faster one? Okay. Well, let's think about it this way, right? Let's think back on what we just did. Okay. So Kruskal's had to do sorting. Okay. But now our sorting algorithm only has to sort integers in the range of 0 to c. Okay. Prims had to use a tree or a priority queue because we had to order the edges somehow, right? Okay. Those data structures don't assume any fixed range of values, right? When we taught you a BST, there was no assumption on the maximum possible integer value that you could be given, right? Same for a priority queue. It didn't matter, right? All we had to do was compare some values. Like all you did was a comparator. Okay. So perhaps we should probably swap that part out, that data structure out for something else instead. Okay. So for Kruskal's, I would say that if you can sort faster, you can speed Kruskal's up, right? We would be bottlenecked by the UFDS. So the best we might be able to accomplish at that point is alpha m, okay? Prims, on the other hand, somehow, if we could find a better data structure, that somehow makes use of this 0 to c assumption, maybe we can also speed it up, right? Identify where the bottlenecks are, fix them, right? Again, I promise you, if you see things this way, you apply the same approach to Dijkstra, you will speed Dijkstra's up, actually, okay, based on this assumption, okay? So here's a warm-up. Given an array, right, of n integers, and here c is constant. Okay, so I'll tell you c is constant beforehand. So c has nothing to do with n. It's not unbounded. I promise you that it will always be at most c. How do we sort this faster than n log n? How should we do this? So just so you know, we're not only potentially improving Dijkstra's now, we're also potentially improving sorting. Okay, so how should we do this? Okay, here's an idea. Why not just count the number of times every integer appears? Right? So in other words, just create a histogram of size c. Okay, so for every possible value that's going to appear, just count how many times it appears. Okay? So it's called counting sort. I know, super descriptive name, right? It's literally what it does, okay? So I'm going to call it histogram. So create a histo of size c, an array called histo of size c. Initialize to all 0, okay? For every element x in the array, right, if it has value x, literally say that, go to the histogram array and just increment its count by 1. What are we trying to do? Well, by the time you've gone through the entire array, histo as the array literally counts the amount of times element x appears in the array. Make sense? Okay? So after you're done with that, the next thing you need to do is iterate on the values. Okay, so iterate through all the possible values. I promise you they were integers from 0 to c minus 1, so iterate from 0 to c minus 1, and output that value as many times as specified by the histogram. Pretty much, right? You go to, let's say value v is at 0, you're going to ask the histogram, how many times did 0 appear in the array? If it appeared 5 times, I will literally print it out 5 times or put it in an array 5 times for you. You're basically just going based on the counts. Okay? Here's an example. I have my original array. I'm going to create my histogram array. Since let's say you promised me that the values are up to 5, I'll create an array of size 6, right? Okay. Go through the entire array and basically count how many times each value has appeared. 0 appears once, so that's 1, right? 1 appears once, so that's 1. 2 appears 3 times, so we put 3. Okay. 3 appears once, so that's 1. Right? 4 doesn't appear at all. I'm going to put 0. Right? 5 appears twice, so I'll put 1. This is my histogram array. Right? Now, to sort of produce the output, we go through the array again and basically just make sure that 0 is output 1 time, 1 is output one time, 2 is output 3 times, 3 is output 1 time, 4 is output 0 times, and 5 is output twice. That's how counting sort works. Okay? So this is counting sort. Question. Okay? This is the algorithm. How long does it take to run? On. Okay, few hands. On for C. Okay. ONC. Okay. O n log n plus C. I think you all know that's not the answer, right? Okay. Yeah, OM plus C. I know C is a constant, so it's actually the same thing, right? But technically speaking, I just want you to know that this thing scales as a function of 2 things. It scales as a function of 2 things. It scales as a function of the number of elements you have. It scales as a function of what the possible max range value is. Okay? So if you told me that the maximum possible bound is really large, right? Like 10 to the power of 6, okay? Now I have to create an array of that size. I actually have to create a million-size array, regardless of how many elements you have. Right? So On plus C is the right answer. Assuming C is constant, this is also On. Okay? But just to be clear, like the more accurate answer here is On plus C. Okay? So we now have a sorting algorithm that sorts things faster, based on our assumption. Okay? The important idea is that we're not really making comparisons, right? I want you to sort of look at this algorithm and realize something. We've not made any comparisons at all. No comparisons. No less than or equals to. You know, I think about it this way: quick sort, merge sort, selection sort, insertion sort, any of the sorts that we've shown you. There was always if this is less than or equals to, it was never about the exact value, it was always about relative values. Okay? I want you to notice something. In this algorithm, there were no comparisons being made. We made an assumption about the input and therefore stopped making comparisons. Okay? Because of the fact that we know something more about the input, we can do that. Okay? Turns out we can apply this idea for MST finding as well. Faster Kruskalls? Well, that's simple, right? Because Kruskalls only needed you to sort the edges. We now have a faster sorting algorithm. Just sort the edges with counting sort. Just. Right? Okay, so basically run Kruskalls, but instead of using merge sort or quick sort or please don't use insertion sort or selection sort, right? But like let's say merge sort, right? Instead of using that, use counting sort. Sort the edges. That's going to take On plus C time. Okay, and then after that, the second half of the algorithm, same thing as before. Run it with your UFDS, right? Okay, so the running time is going to be C plus M alpha n time or alpha m, whichever one you want. It's about the same, right? Okay, does this make sense? Does this make sense? I don't know if you know, we've sped Kruskalls up, right? It went from m log m down to this running time. Okay? Now, at this point, if you tell me, but then what if C is very large? What if C is like m squared? Okay, then don't use this algorithm. Like, please don't use this algorithm, right? Okay? Let's try doing the same thing for prims, right? We now want to modify prim's algorithm, but we can't use a balanced binary search tree or priority queue. That's too slow. Right? It's bottlenecked. We're literally bottlenecked by the fact that these data structures only do comparisons. It's not making use. It's trying to order the edges for you, but it's not making use of the assumption that we had. Okay. So here's an idea. Why don't we just use C different queues or stacks? It doesn't really matter, but queue or stack, right? Okay. So if you know that the edge weights can go up to C, let's just make 0, 1, 2, 3, 4 until C minus 1 of those queues. Okay. Every time you see an edge of weight W, you're going to put it in the Wth queue, right? So if I see an edge of weight 5, I'll go to the 5th queue and I'll put it in that one. Okay? So we need to do a few things because remember, prims had to do two things. It had to do insertion and find min and remove. It had to do extract min, right? Basically, it's extract min. Okay? So question: given this data structure, how long does it take to find the smallest edge stored so far? O1, OC. Few hands. O log n, On. Okay, good. OC is the answer, right? You have C queues, just go through all of them, find the first non-empty one. The first non-empty one is the minimum weighted edge so far. Great, right? So to find the minimum weighted edge so far, just iterate from 0 to C minus 1, and the first non-empty queue that you see, pop from it. Or DQ, whatever you want to call it, right? C++ is really horrible, by the way. They call it pop for Q, and it's like, no, you should call it DQ. Anyway, sorry, random thing in my head. Had to get it out. Okay, so now we have our replacement for a priority queue / balanced binary search tree, right? Instead of this fancy data structure we taught you, just use C queues, because why not, right? Okay, so prims, but a little bit faster, right? Most of the algorithm is the same as before, actually. Most of the same energy, right? It's literally the same algorithm. You're just swapping out the data structure, right? So basically, create an array of those queues that you have there, and basically use that instead of your priority queue or balanced binary search tree. Okay, question: what's the runtime? VAS. VAS is the runtime. M log m. Of course not, right? If not, why would I be showing this to you? M plus C? MC? Okay, yeah, pretty much, right? Okay, good, great, right? Why? Well, because finding the minimum now takes C time, right? Okay, so you have to do that for all M edges. So in the worst case, right? So let's see, right? Creating this OC time, right? Creating this array of C empty queues, that's going to take OC time. Okay, same thing. Find the minimum node out of the current thing. Also OC time. That's something you guys know, right? Doing this, checking whether it's marked in the tree, same as before. O1 time, right? Going through all the neighbors, O degree V time, which means you're gonna have OM iterations here, right? So OM times OC. Well, that's OMC. That's OMC, pretty much. Okay. So this is how much it costs. Knowing the algorithm, priceless. Right? Yeah. Anyway, for constancy, this is OM time. It's faster. Make sense? Make sense? So this is even better than Kruskal's, right? Okay. If you add early termination, this thing can be done in ONC. There's a way to do it, but yeah. But if the graph is dense, we still have to add all the edges, so pretty much this is the bottleneck. It's still ON plus MC, pretty much. Okay? I'm going to tell you a funny story now. Well, maybe you won't laugh, but here's a funny story for you. So while I was preparing these slides, which I promise you was not 2 a.m. because I had more time. After I had to take a break from setting your finals. It was difficult. Right? Okay. So funny story. Maybe not funny, but funny story. I tried to optimize this algorithm down to log Cn plus m. I tried to do that for you guys. If I did, you would have seen a very cool algorithm, right? Okay. Now the thing is this: no one's done it before. I googled it, I couldn't find it, right? So for once, you'll actually catch me talking to an LLM, right? I'm an LLM doomer, by the way, right? So at some point I said, oh, you know, instead of using CQs, why not let's just use a size C balanced binary search tree, right? Because then you can shave off the C to log C, right? Makes sense, right? I mean, come on, like obviously. Right? So I asked Gemini because I needed, okay, look, you know, I needed to run it by someone, and you know, so it said, this is an excellent observation. You absolutely can use a balanced binary search tree like a rib-black tree, AVL tree, or built-in set to achieve the exact same m plus n log nc time complexity. In fact, conceptually, a BBSC does the exact same job as the segment tree in this context. Okay? So this is what it gave me. I was very happy. I made the slides, by the way. They're deleted now, but I made the slides, by the way. Okay. It even got praise, right? Because then I asked it, okay, look, the text is a bit small, the text is a bit small. I'll read it out to you, right? Basically, I tried to analyze how large the C can be. Let's be honest here. After I talked to you about counting sort, right? What did I say? There is a limit to how large C can be before the algorithm slows down. Makes sense, right? Okay, so I asked it, I said like, hey, doesn't this mean C can be exponential in n? Because it's log C, right? So, you know, we could do like 2 to the, you know, like 2 to the square root n or something. That'll be, C can be really large now, right? And then it goes, right? Like, you are making a really clever mathematical, leap here by connecting the number of edges to the number of vertices, right? And you go, but there's a slight catch, okay? But generally, you have great intuition, right? Okay. 5 minutes later, I realized my algorithm doesn't make sense and there's a way to break it. So I asked it, wait a minute, if the balanced binary search tree is of size log C, that doesn't make sense because now we can hold all n edges again because C can be much larger than n. A size C balanced binary search tree still needs to process at least n nodes, right? That's still, like, I made the slides, I was very happy, you know, I actually like closed the tab and I was like, okay, time to go to sleep, right? Then I got off my chair, right? And I was about to like climb into bed and I was like, no, that's wrong. I literally went back, I logged in, I pulled up the chat and I said, wait, this doesn't make sense, right? Okay? And then it goes like, you're completely right, you just caught a massive fatal flaw in my previous logic. Okay? Right? So what am I trying to get at with this? Like, look, granted, the maestros among you out there are probably far better than prompting ChatGPT or any LLM than I am. I'll give you that, okay? And also, this is Gemini 3.1 Pro, free tier. I have no money. You can, you know, like, yeah, okay? I will say this. I don't think I want you guys to, okay, let's put it this way. I'm not trying to discourage you guys from using LLMs, right? I do, like, look, you know, all of us are having an existential crisis. What can we still do now that LLMs are so good, right? Okay, and it's not to say that maybe, you know, Google is going to find out and their Gemini, I don't know, 6.7 Pro, like free tier, someday is going to be like, oh, Eldon, you made a mistake, like immediately on the spot, right? I'm not going to tell you that it won't ever be good, okay? But I do want to say something, which is that I do think AI is great for automating away tedious work. I don't want it to automate away your thinking. Even if you can do something, I think this is a great example in how it can literally confirm things that aren't true still, right, if it's complex enough, okay? So you still have to think for yourself about what it's giving you. You still have to think for yourself about what you're doing, right? It could help you do sanity checks, maybe. I'm going to be honest. I wanted this to be my sanity check, and somehow it still failed. I still had to sanity check myself, right? No thanks to this dude right here, right? Like, I could have given you a very wrong algorithm with very wrong slides here today, okay? So, look, automating away other work, like, for example, you wanna you have like a spreadsheet, you want to say, okay, I want to figure out what the 75th median and 25th percentile is in an Excel spreadsheet formula. I do that for your grading, by the way. I literally have to, with your final grades, I have to count on these formulae. To me, it's kind of like, okay, that's a no-brainer, right? And sometimes I need to do something very complex on top of that on the spreadsheets that contain your grades. Fine, I'll ask Gemini. I'll be honest, I'll ask Gemini. It's tedious work. Do I need to count the formula myself? No, right? But in designing algorithms, would I trust this dude over myself? Probably not, okay? Not yet, at least. So even if you can do it, please don't let it automate away your thinking. You can let it automate away work that you don't want to do. Please don't let it automate away your thinking. Please. Okay? Okay, so now that I've mentioned that, that was an aside, right? Okay, I beg you, really. Coming back to this, so in case you're curious, because we try to speed up MST finding, the state of the art, by the way, happens to be a bit complicated. We have a randomized OM time algorithm, which is very cool. So an expected runtime OM, and it's comparison based, so no assumption on the weights. No assumption on the weights, okay? There is also an algorithm that is not randomized and slightly worse, very slightly worse at M times alpha M, and it's comparison based. So it didn't make the assumption that we did, and it still hit the same time complexity. That's insane. Okay, the one that we came up with today kind of looks like that on the third row. Yeah, a bit boring, you know, we assume C weights or whatever, right? Now here's the funny thing when I was making these slides for you guys, okay? Why? Oh, right, okay, so, why did it turn off? It shouldn't turn off. Hello, okay, it's back, right? So, the very final row there, right, the projector was surprised I stood up. The very final row there, right, when I was Googling this, right, it turns out there, wait, what are you doing? What are you doing? I'll sit down if you want. Okay, right? So it turns out that the very final row there, right, there is an algorithm that's proven to be optimal, deterministic, right? Okay, look, the range is really small now, right? So you have a randomized algorithm that runs in OM time. This is the fastest it can be. You have to look at all the edges anyway. So OM time is optimal, but it happens to be randomized. And you have a deterministic algorithm that runs in slightly slower time, M times alpha M. Okay. These two people right there came up with an algorithm. They proved that it was optimal, but they couldn't give the runtime. Do you know how ridiculous that is? They literally gave a proof for the algorithm and said, look, our algorithm is the fastest possible asymptotically. Okay, great. What's the runtime? I don't know. How? I don't know how. So the answer could be somewhere. The answer could be somewhere in between OM and OM alpha M. The gap is really small. Okay, like the answer could be in there. For all you know, right? It's like M log alpha M or OM like square root alpha M. I don't know. We don't know, right? Like maybe you can prove it. Like it's optimal. We just don't know what it is. That's ridiculous, right? So if you bound this, you like anyway, right? That's the state of the art. Okay. I also have a challenge for you. You can actually speed this up. The algorithm I showed you today. You can actually speed this up to ONC plus M. There is a way to do it. You already know how to. All right. Okay. Few more things to mention. Where does the party end, right? So I show you a bunch of state-of-the-art stuff. I show you a bunch of basic speed-ups, but there are definitely a lot that exist out there. Okay. So where does the party end? I'm going to make a few observations for you. You might have noticed that since week 1 until now, a lot of the algorithms and data structures that we use, like I mentioned just now, does some form of comparison, right? Your binary search tree, it does like a compare the key. It's greater than, smaller than, equals that, like or equals to. We do something on 3 cases, only 3. You assume nothing about the input, right? Okay. So for example, balanced binary search trees, they compare keys. It uses a compare. You all know comparators from 2030S, right? They literally made you guys write Yes, no, yeah, yes. You know what comparators are? Kind of. Okay. I see a few awkward nodding. So the rest of you who don't know, right? You're probably behind. Maybe. Right? Okay. But okay, in Java there's a comparator class. You use it to instantiate your data structures, right? If you want to sort, you have to give it a comparator class. You don't have to do it for integers because that's the default one, right? Okay. For balanced binary search trees, you compare keys. When I say compare here, I mean less than or equals to or greater than, right? Okay. Sorting, you compare elements. In your priority queues, in your heaps, you compare priorities, right? We didn't care what the thing you were storing was. I gave you integers as examples, but you could have put fractions, you could have put strings if you wanted to, okay? Your single source shortest path compares distances, right? It literally, your edge relaxation or your path relaxation literally has a less than, before you set the weights, right? MST, right, the first version we show you, compares edge weights. It's literally just a less than or equals to thing, okay? Up until that point, before I show you these speedups, we've really not made any assumptions about weights, elements, or priorities, right? All we needed was a comparator. Okay, so you could put strings if you wanted, you could sort strings if you wanted to, for example.
You might wonder if there's a speed limit, right? Because like n log n, for example, is like, why didn't I show you a faster algorithm? Why did our sorting algorithm stop at n log n? Why did balanced binary search tree stop at log n? Why not log n? Why not square root of log n? Why not log n over log n? These are all functions that are smaller than log n. Why none of these things, right? So for example, your quick sort merge sort, like stop at n log n. Your balanced binary search tree stops at log n. Why not have sorting at on, right? After all, think about it, right? Your array of size n only needs linear time to go through all the elements. It doesn't need n log n time. There's this extra n log n factor. Isn't that kind of like a bit like, not lean, right? Okay. Why not have a balanced binary search tree that does insertion at log n time? Why not? Okay. So it turns out that if you only use comparisons, like in other words, you only have a comparator less than or equals to or greater than or whatever, right? One of those, okay? This is a hard limit. It actually is a hard limit. You can't insert into a balanced binary search tree with a better worst case guarantee than log n. You simply cannot. It's provable. You cannot. You can't sort an array faster than n log n in the worst case, right? I know in the best case, you call insertion sort, your array is sorted, it's on times. Yes, I agree. But in the worst case, without any of these sort of best case scenarios, the worst case happens to be n log n time. You can't extract min faster than worst case log n. You can't. You simply can't. Okay? So I don't know how many of you know this about physics. I hope this is sort of a universal thing by now, right? The speed limit of the universe is c. The universal, like the speed of light, c, right? Just like how that's a fundamental truth about how things work physically in the universe, right? These colored lines that I have here in what magenta, purple, and blue are the computer science versions of speed limits. You just can't, like no matter how hard you try, there's no way you're going to design an algorithm or a data structure that's better than these. It's provable. It's provable. These are our speed limits. So someone outside of computer science can't come to you and say, by the way, I want a data structure that does insertion better than log n. Give it to me. You can't. You simply can't. If it's comparison based, you simply can't. Okay? There are still many problems we don't know efficient algorithms to. That's also a thing. Okay? But somehow we do have these speed limits in place. It's provable. Okay? There is still a lot to learn. You will actually see a proof of some of these facts in 3230. They will actually prove it to you. They will actually prove it to you. Okay? So what are we going to do? In light of this, what are we going to do next week? Next week, we're finally going to begin our journey on moving on to actually hard problems that we don't know good algorithms for. I'm going to start showing you problems that we don't know good algorithms for. Okay? I'm going to show you basic techniques to make these problems acceptable to solve in practice. Okay? In other words, dynamic programming. If that's it, see you on Wednesday. That's all I have for you today.